Okay, so now we'll look at the queue ADT. Now, the logical view of a queue is it will operate in a first in first out fashion. So, the first element you put into the queue is what the first element to come out of the queue. Okay, so let us say you have a queue like this. So, first you going to put 30 in it, and then 71 and 42 and so on. So, 30 stays in the front of the queue. So it's like a grocery store queue. So whoever joins the queue first is in the front of the queue, and then the person who joins the queue after that will get next to it, and so on. So the end of the queue is the last element that you added to the queue. So we call the operations as NQ and DQ. So NQ is adding an item to the end of the queue, and DQ is removing an item, deleting an item from the front of the queue. Now you can also do a peek operation, which is reading the item from the front of the queue, and then you can also check if the queue is empty or not. And we would prefer to do all these operations in constant time, big O of one time. Okay. Now you could implement the queue using any of the three data structures you have seen, which is like a dynamic array or a single linked list or a double linked list. Now, if you use an array, you would need a big O of n time due to the need for resizing when the queue gets full. In the case of NQ, because it's similar to insertion. Now, for a DQ, that's similar to deletion. You have to remove things from the an element in the front of the array, means at index 0. So that's the front of the queue at index 0. Then you have to really shift everything from one position to the left. So that is like a theta of n time complexity. Peak, of course, you can read at any index, including index 0, so it can be run in constant time. So both NQ and DQ with an array will take big O of n and the theta of n times. So it's not really a good strategy to implement a queue using an array. Now, if you try to implement a queue as a single linked list, now if you maintain the front of the queue as the node next to the head node, then you could uh, uh, if you do that, I'll take the other way. So in the case of like implementing a queue as a single linked list, you have to enqueue, right? So that means you have to add things to the queue. So the queue next to the head node will be the front of the queue. So that means you have to, if you want to insert, you have to start from the front of the queue because it's a head node. Next to the head node, you have the front of the queue. So you have to start from the head node and traverse the entire list. And then once you reach the end of the list, you do an enqueue or insertion at the end of the list. So every time you have to insert, you have to traverse the entire list and then do the insertion. So enqueue will take theta of n time. Of course, if you maintain the node next to the head node as the front node, that's similar to how you did the stack. You could do the deletion or the DQ in constant time, but NQ is going to be still time consuming. Okay. Now, it won't make much sense to do it the other way, in the sense that to maintain the end of the queue as the front of the queue. So in that case, to do the DQ, you have to traverse the entire list and then DQ that node. In that case, NQ can be done in constant time if you maintain the node next to the head node as the tail of the queue. Yes, you can do it in constant time. So either way, either NQ or DQ is going to be time consuming. So that's why a double linked list based implementation is a preferred strategy to implement a queue. So as we follow user convention in the stack, we will maintain the or we will insert at the tail end of the queue. Now you could also do it at the head end of the queue. So we will say we will enqueue by inserting the new node from the tail of the list. and dequeue by removing the node from the next to the head node. So that in that sense, the node next to the head node will be considered as the front end of the queue, and the node next to the tail node will be considered as the end of the queue. So let us look at this implementation of a dynamic array first. I'm not going to show the code for single linked list. After that, I'm going to show the code for double linked list. Alright, so the code for a dynamic array based implementation, you have say 10, 7, 5, 9 as a queue. So 10 is the front of the queue at index 0 and 9 is the end of the queue at index 3. Okay, so you maintain the three member variables: array pointer storing the base address of this block of integers array which as a queue, max size is in this case is 7 and end of queue is 3, storing the index of the last element that you inserted to the queue. So how you initialize the queue content? So array is like storing the base address of this block of integers of size, max size equals size, and then end of queue is -1. So queue is kind of initially empty. You have just set up the array. So you can use this condition, end of queue is now equal to -1, that means the queue is empty. Okay. Now you can resize as before. So enqueue operation is to add insert at the end of the queue. So you check whether end of queue is equal to max size -1, that means array is full, so it's time to resize it by doing it 2 times max size. Then after you have resized the array, then you can do the insertion. So plus plus end of queue will increment end of queue first, and then array of that index and new end of queue you set the data. Now dequeue is like you have to remove the element at index 0. So if end of queue is greater than or equal to 0, you can really do the dequeue. If end of queue is like less than 0, you cannot dequeue, you can just return an invalid value. So you store the element at index 0 in a return val, a temporary variable, because you're going to shift everything to the left and that value at index 0 will get overwritten. So index, then run a for loop, index equals 0 to index less than end of queue. So array of index is overwritten with array of index plus 1. So whatever is at index plus 1 will overwrite the value at index. So keep shifting to the left basically. And then so with this kind of overwriting, you have basically deleted this array of 0, whatever the value is. So the array size, the queue size has decreased by 1, so you should kind of imitate that by doing end of queue minus minus. So even though that value will be there, so for example, if you do end of queue, it will do like what? Instead of 10, you have 7, and then instead of 7, you'll have 5 here, and instead of 5, you'll have 9. So this 9 is still there in the memory, but when you do end of queue minus minus, end of queue will become 2. So that is from 0 to 2 is the accessible portion of the queue, and this 9 kind of considered not accessible because it's outside the range of the queue. Okay, so then you can return val, because that's the value, that's the variable that is storing the value of the element at index 0. Then you can do a peek operation by checking if end of queue is greater than or equal to 0 or not. If it's greater than or equal to 0, that means the queue has something in it. So return array of 0, else return an invalid value. Okay, so let me stop this video.